Stop that. All right, I am so set. And I'm going to begin by fixing my bad arithmetic from last time. Yeah, so are you reporting?
I am now, yeah.
Okay, great.
Want me to stop it?
No,
Okay.
it's fine.
I didn't know if you were going to say that.
I'm just embarrassed by it, but that's completely irrelevant and actually kind of silly. But there you are. As long as I never have to look at the recording, I'm good. You know how your voice always sounds not like you?
Yeah.
All right, it's 3:30, so let's get started. The plan for today is to fix my arithmetic errors from last time, which are just ridiculous, and I'll totally explain that. My arithmetic errors from pages 266 to 7, and then my arithmetic errors on the example prob that I was doing for the uncertainty in the energy for a coherent state. And then we're going to go through the other parts that we didn't yet go through from chapter 7 and finish up with some more example problems. And that may take more than today. In fact, I expect it to. I expect this to also go through Wednesday. Next week, we're going to do chapter 8. And chapter 8 is a short chapter, but there's a lot of stuff in it. And I've already posted the P-set for chapter 8. There's only going to be one, and it only has 3 probs on it. But they're a little bit longer. 2 of them are a little bit longer than usual, so they're going to be like double credit. So it's still going to be a 20-point P-set. And I don't think chapter 8 is long. Hey, welcome. I don't think chapter 8 is long enough. That is, I think it leaves out a lot of explanation. So I'm going to fill in a lot of stuff. And it's one of my favorite subjects, quantum mechanics and path minerals. So be prepared to be bored. Okay, and in fact, that may be 3 classes, even though we're only having 1 P-set on it. So I'm apologizing in advance. So that's the plan. Before we begin, are there any questions? Okay, so I'm missing P-sets from several of you, and it would be good if you kept up more, and that would be good. If you need help, please contact me, and I'd be happy to help. But once you sort of fall behind and start having, I've got 5 P-sets to make up, it's kind of hard to catch up. So, not meaning to embarrass anybody, but it would be good to do that. All right, so first let's fix my bad arithmetic, okay? So my bad arithmetic started when I was going through what the delta x squared, that is the uncertainty in x and the uncertainty in px are for a coherent state. And so I'm going to just go through slowly and fix. All right, so for x squared, obviously this is h bar over 2m omega, and this is in the coherent state alpha. So this is a plus a dagger squared alpha, and I've already squared the constant out front. Now, a plus a dagger squared, of course, is a squared plus a dagger squared plus a dagger plus a dagger a. And the screwy thing I was doing was saying, oh, a dagger a and a dagger both give us absolute magnitude alpha squared, and they don't. Okay? So I was just doing too much in my head and not being careful. This is what we know. We know that A operating on alpha gives us alpha times the same state back again. That's the definition of the coherent state. And if we take the dagger of this equation, we get the dagger of this side, which remember is the dagger of each, but reversed. So this is going to be A dagger, right? And this is alpha star, right? And I took the alpha out, so it's just a constant, it doesn't matter in what order those two things come. So we only know the action of A dagger on alpha going this way, on the bra. We don't know the action of A dagger on alpha on the ket. And so I was mixing these up because they're in different order, okay? So in order to be able to figure out what the action of the product is in the wrong order, this guy's in the wrong order, right? What do we have to do? We have to put in the commutator. So A dagger is equal to 1. And that's on page something or other. Something or other. It's really near the beginning of the chapter. Hold on, I'll find it. Yeah, this is equation 710. So this is A dagger minus A dagger A, by definition of the commutator. Okay? And so that gives us an equation for what this guy is that we don't know what to do with. In other words, A dagger is equal to 1 plus A dagger A. Because this is equal to this. So I can substitute that in here. So this is equal to h bar over 2m omega alpha A dagger squared plus A squared plus A dagger squared plus this guy, which is 1 plus A dagger A plus A dagger A, and then operating on alpha. Now if we consider the action of each of these things in, dagger A. Forgot the little hats here, sorry. Okay, now if we consider each piece in turn, because it's just the sum of each of these 1, 2, 3, 4 pieces, okay? So A squared operating on alpha is just A operating on alpha, which is just alpha squared alpha. Not alpha absolute magnitude squared, but alpha squared. And A dagger squared operating on the bra alpha gives me exactly similarly alpha star squared. So I know what each of these things does. That's very easy. Then 1 is just 1. So I just have 2 of these guys. So A dagger A between alpha and alpha, between the bra and the ket, I get, from this part I get alpha alpha, and from this part I get alpha star. So this whole thing then equals h bar over 2m omega. Let's see, alpha squared plus alpha star squared plus 1 plus 2, because there are 2 of these guys, times alpha squared. So this time I've done it right. And in fact, if you look at the book, on page something or other, wherever we were, that's exactly what they get in equation 789. Okay, I was mixing them up by not being careful. And I guess this is a good sort of object lesson. Number 1, professors make mistakes. And number 2, be careful. Of course, you already knew that. Okay, so I hope you now believe me when I say that if we do p squared in the alpha state, this is minus I square root m omega h bar over 2 quantity squared alpha, let's see, alpha A minus A dagger, A minus A dagger quantity squared. Okay, and this is, of course, minus, excuse me, no I, the I goes away, but minus m omega h bar over 2, and then we have alpha a squared plus a dagger squared minus a dagger minus a dagger a. And we've already figured out what all those things are. So, I really need to be tall. This is minus m omega h bar over 2 times alpha squared plus alpha star squared. Let's see, okay, so this one is going to be 1, so with the minus sign, it'll be minus 1 minus a dagger a. And then, so we've got minus 2 a dagger a's and a minus 1. So this will be minus 1 minus 2 alpha squared. And that is exactly what they have in 790, except they've taken the minus sign from the minus m omega h bar in. Right. So, okay, so then they just multiply them together, okay, on page 267. So on page 267 we get delta x squared, oh, well, they do multiply them together, but first they figure out delta x squared, which is average of x squared minus average of x squared, which is, this is the x squared here, h bar over 2m omega alpha squared plus alpha star squared plus 1 plus 2 alpha squared. And then we subtract the average of x, which we did successfully find last Wednesday. So that was, I'm looking for it here. And I'm not finding it. Oh, here it is. All right, so this is minus, right, so average of x is on page 265. So the average of x was square root h bar over 2m omega alpha e to the minus I omega t plus alpha star e to the plus I omega t. Okay, and so when we square that, and you can just think of this as alpha of t, because all these alphas are alphas of t, and this is alpha star of t. So when I square that, I get x squared, equal h bar over 2m omega alpha squared plus alpha star squared plus 2 alpha squared. I'm just multiplying. Okay, so minus, and I'm, this is alpha squared plus alpha star squared, minus 2 alpha squared. And so this guy cancels this guy cancels this guy cancels this guy, and all the time dependence has gone away. So this is just h bar over 2m omega. So the uncertainty in x does not change with time, which means we don't get a spreading out of the wave packet in the coherent state, which is why we call it the coherent state. Similarly, the average of p, all right, and I'm going to look it up in the book again. The average of p is minus I square root of m omega h bar over 2, and again it's the but it's going to be alpha minus alpha star instead of plus. And so average of P quantity squared is minus M omega H bar over 2 alpha squared plus alpha star squared minus 2 alpha absolute magnitude squared. So that means that delta P squared, which is average of P squared minus average of P quantity squared, is H bar, minus M omega H bar over 2. You know what, I'm going to take in the minus sign just the way they did. Minus alpha squared minus alpha star squared plus 1 plus 2 alpha squared. And now this is going to be minus a minus, which is a plus. So that's going to be plus alpha squared plus alpha star squared minus 2 alpha absolute magnitude squared. So just as with the x, we see that the all the time dependence goes away, and all we're left with is this. So delta P squared is M omega H bar over 2. So delta X, delta P is square root H bar over 2 M omega, square root M omega H bar over 2. And as you can see, the M omegas go away, and the H bar omegas over 2 just multiply to give H bar over 2. So this is a minimum uncertainty state, okay? Because this is, in fact, the minimum uncertainty that's allowed with X and P, because they are a maximum uncertainty pair. And that's so H bar over 2 is exactly the same minimum uncertainty as you get with the ground state, and we're going to talk about that also. Okay, so now that my arithmetic is fixed, it all makes sense and it all agrees with the book. Yeah. All right, I'm now going to do, redo rather, problem, all right, where did I put them? Oh, there they are. I'm going to redo problem 22, which I started out doing and then screwed up. So, here it is. And I'll point out where I was making the error, and you'll see that it was exactly the same error. So, in number 22, we have the coherent state alpha, and we want to calculate both the average energy and the uncertainty. Now, I did the average energy okay. So in 22, we want to calculate the average energy, which in the coherent state alpha is alpha E alpha. And we remember that that the energy here is A dagger A plus half times H bar omega. That's just the Hamiltonian in terms of the raising and lowering operators. And just as we had before over here, right, where I did it over here, this just gives us absolute magnitude alpha squared for the A dagger A part, and then we have a half. So this is H bar omega times absolute alpha squared plus a half. So I did that part correctly, and in fact I can hardly do it wrong, it's so easy. But now let's do E squared, and you'll see that I was making the same error, okay? So average of E squared in the state alpha is alpha, and then H bar omega quantity squared times alpha dagger A dagger A plus 1/2 quantity squared. And those are operators. I should put little hats on them, sorry. Oh, and alpha, which is H bar omega quantity squared. And alpha, and then we've got A dagger A dagger A, that's the same term, right? Plus 1/2 A dagger A, that's from this one, then plus A dagger A, sorry. Plus 1/2 A dagger A from the other, right? And then plus 1/4. Amazing, I got the same thing here. Okay, now let's figure out what we're doing here, okay? And I screwed up because I thought this was absolute alpha quantity to the 4th. Right? And that's wrong, okay? Well, okay, you have to take it down several steps. If we have A dagger operating this way, that gives me an alpha star, right? So alpha, A dagger, A dagger, A. I'm just doing this term here. So this one gives me alpha star, alpha, A dagger, and then this one gives me alpha. Right? But now these guys are big roots. That's the error I made. Do you see this? Yeah. So what can I say? So this gives me, so this just one term gives me absolute alpha squared, but then we just are left with A dagger. So we need to use the commutator again to put this in the right order, okay? So remember that the commutator of A with A dagger is 1. So this is A dagger minus A dagger A. So in other words, A dagger is equal to 1 plus A dagger A. So I'm doing the same trick. So this is the same thing as absolute alpha squared, alpha 1 plus A dagger A alpha, which is alpha squared 1 plus alpha squared. So my error here was, I mean, this does in fact give me an alpha absolute magnitude to the 4th, but it also gives me a factor of alpha squared. Okay, now for these two terms, I know exactly what happens because they're in the right order. So I just get an alpha absolute magnitude squared out of each of them.
I think I have a question. Do we get the exact same term twice? You have 1/2 of A dagger A.
Well, that's because I'm squaring it. So it's A dagger A plus 1/2 times A dagger A plus 1/2. And so I've got this one times this, and I've got this one times this. Yeah, I mean, I should have just combined them. In fact, let me do that. There. Everybody happy? Okay. So this one just gives me an alpha squared. Absolute magnitude squared, excuse me. So this whole thing gives me alpha squared times 1 plus alpha squared. That's from this term. Plus alpha squared absolute magnitude plus 1/4. Or, multiplying it out, alpha to the 4th plus 2 alpha to the square, absolute magnitude plus 1/4. Good? All right. So, I'm switching over to here now. So, if I want my delta E squared, that's average E squared minus average of E squared. And I've got my average of E squared, which is alpha to the 4th plus 2 alpha absolute magnitude to the square plus 1/4. and then I subtract, oh, sorry. Forgot to bring along my h bar omega quantity squared. Sorry. Now I want to square this guy. Right? So this is minus h bar omega quantity squared, and then the square of that guy, which is alpha squared plus 1/2, I hope, yes. Okay, which is h bar omega quantity squared times alpha squared plus 2 squared plus 1/4 minus alpha to the 4th, that's the square term there, plus 1 times alpha to the square, plus 1/4. Oops, miscopied this. All right, looks good to me. Everybody okay? Yeah. All right, so now I can cancel this guy out with this guy. I can cancel this guy out with this guy. And I have 2 absolute alpha squared minus absolute alpha squared. So that's just an alpha squared. So this is h bar omega quantity squared alpha squared. So that if this is delta E squared, then delta E, which is what I wanted to begin with, is h bar omega times absolute alpha. So that's the uncertainty in energy if you happen to be in the alpha state. Okay, I've now fixed all my horribleness from last time. Woot woot. Any questions on that? Right. I was just not being careful, and that can be deadly when you're doing physics. Or mathematics. So I should have been more careful. Okay. All right, I now want to go through example 7.4, and because that intimately relates to problems numbers 21 and 24, which I also want to do for you. Sorry. Okay. Please interrupt me if you have any questions or if anything is unclear. I mean, if something is unclear, maybe I made a mistake. I mean, I do make mistakes. It's kind of obvious. Okay, let's talk about example 7.4 just briefly before doing the 2 probs that are about that. Okay? So, example 7.4 is about the ground state of the harmonic oscillator as it relates to the coherent state. Okay, so this is actually explicitly a problem in the, I think it's number 23. No, excuse me, number. Well, it's in my notes. We'll get to that. Okay, let's do the example first. Here's the ground state of the harmonic oscillator in X space. It's the Gaussian, as you remember. So this is m omega over pi h bar to the 1/4 times e to the minus m omega x squared over 2h bar? Yes, 2h bar. All right, so that's the ground state energy eigenfunction of harmonic oscillator in X space. And the first, and the prompt is to show that we can generate the coherent state alpha by simply displacing the ground state from its equilibrium position by a distance d. And it's illustrated here, and I've already shown you this picture a couple of times. This is what the ground state of the harmonic oscillator looks like. It's Gaussian. And if I displace it by a distance d, it's going to oscillate back and forth, as opposed to just sitting there in the center. So how do I displace something? Well, I use a displacement operator, what we call the translation operator, t hat. And we're displacing it at a distance d. And you'll remember from chapter 6, and I wrote down the page here, this is equation 626, page 197. So this is e to the minus I p sub x d over h bar. Now here, p sub x is an operator, and d is just a number. It's the distance I'm displacing things. P sub x is the generator of translations in the same way that J was the generator of rotations. So compare in your head our rotation operator, what do we call it, R? I think we called it R of theta. And this looked like e to the minus I J, let's say in the z direction, and then phi, this is the angle over h bar. And so this was the generator of rotations around, well, in this case, the z-axis. Okay, this would rotate your state an angle. Oh dear. If it's going to be phi, it's got to be phi. All right. So this would rotate your state an angle phi around the z-axis. Okay. So similarly, this was the generator of translations, and what it would do when it operated on a state x was just turn it into state x plus d. And if you don't remember this, just go back at chapter 6 and look. It's exactly analogous to this thing which we spent chapter 3 doing, and so on. Okay. So I hope that looks maybe a little bit familiar. Okay. But this was the thing that we had. Now we already know what the p operator looks like in x space, so we can write t of d, which is this, as e to the minus I d over h bar, and then px, remember, is minus I square root m omega h bar over 2 a minus a dagger. I always have to look that up to make sure I get the constants right. But, yeah. So I can just plug that in. So this is minus I m omega h bar over 2 a minus a dagger. Now the minus i's multiply, of course, just to give you a minus sign. So I'm just going to multiply those out. And we just get that. If you like, you can take the minus sign inside and just have a positive exponential, because this is a minus a dagger. And I think that's what he does. Yes, he does. He takes that inside, and then he has a dagger minus a without the minus sign. So that's the first equation at the top of page 268. Okay, so we're going to apply t of d to the ground state wave function, which is this. So I'm going to take this whole thing and operate on the zero state. Okay. And if I do that, what happens? Well, as you maybe can see, we get I want to relate this to the here it is. Here it is. This is equation. This is problem 21, where he asks you to do pretty much the same thing. So C, Rob, 21, which we'll finish after we finish with this. All right. So we know what d of alpha is, because we've already defined that in I will get there. So this is the same thing as, if I put in the x, this is the same thing as m omega over pi h bar to the 1/4. And then all this does is just advances us an amount d. So all we do here is advance a d. So this is e to the minus m omega x plus d quantity squared over 2h bar. Okay. Now how do we relate this to the operator that they're wanting to define here, which he calls capital D? So let's do that now. So we're defining capital D. I'm still in the example on page 268. So he says, it is helpful to introduce a generalized translation or displacement operator, capital D, so whatever. So here we're defining D of alpha, defining that as e to the alpha A dagger minus alpha star A, where those A and A daggers are in fact the operators that we're used to. And if we compare this, we can see that T of D, excuse me, which is e to the d over h bar square root m omega, I guess I should put the h bar in, 2h bar A dagger minus A. So notice that we get that this thing is the same as that thing if we identify alpha as d times square root m omega over 2h bar. Now, in this particular case, alpha is real, okay? But you know, as time goes on, it becomes complex, as we noted last Wednesday. But okay. All right. So this is the same as this with this alpha. And now what we're going to do is operate with d of alpha on the ground state 0. Right? So this is e to the alpha A dagger minus alpha A, alpha star A. And we know from problem 19 that this is the same as, times 0. So we know from problem 19 that this is the same as e to the alpha A dagger, e to the minus alpha A, e to the minus A dagger comma A over 2. So this is problem 19, which we did in class on Wednesday, I guess. Okay. Now, we know what the, commutator of A with A is 0. There we go. When I do something stupid, point it out, right? Right. Now, what is the commutator of A dagger with A? Well, that's -1, right? Because the commutator of A with A dagger is +1. So this is -1. Right? And now we finally get exactly what we have up at the top of page 269, which is that this is equal to e to the alpha A dagger, e to the minus alpha star A e to the plus, oh dear, I forgot the alphas. E to the plus alpha squared by 2. So, oh, with a minus, extra minus sign. Right, so that's minus. Extra minus sign because there was a minus sign here. Okay, so that's true for problem 19. Now, we can actually put in what each of these things is, and that's what gives me the final equation 269, when these guys operate on the 0 state. Okay. Because we know what these guys are in terms of the Taylor expansion. Okay. All right. That's equation. That's example 4 from the chapter. And now let's go on and finish this with problem 21. So problem 21, which is most of this. And then now we're just going to finish problem 21. Problem 21 says, show that the average of x is d cosine omega t. That is, the average of x goes like the cosine, exactly like that picture, for the coherent state where this is t of d 0. Okay. Okay, so let's do that. So just as we saw over here, we know that t of d is equal to that stuff there, and that's d of alpha. Then all we have to do is plug in from equation 786. I wrote it down here someplace. And 786, remember, was if we have an average of x, which is some coherent state that this was equal to square root h bar over 2m omega alpha e to the I omega t plus alpha star e to the minus I omega t, and then that was reduced to square root h bar over 2m omega 2 absolute alpha not squared cosine omega t plus delta. Now the delta is the offset. That is alpha was defined as its magnitude times e to the I delta. But remember, the alpha here starts out at t equals to 0 for being real. So that means the delta is 0. So here, delta is 0. And the alpha we have right here. So x, average x, then is square root h bar over 2m omega 2 times alpha, which is d square root m omega over 2 h bar, and then cosine of omega t. Okay, so the h bars go away, the 2's go away, the m goes away, and the omega goes away, and we're just left with d cosine omega t. So 21 was real fast if we just stole what we already did in the example. Okay, it's also related to 24, so let me do that one too. I don't know why he doesn't put these in order. But whatever. Do these things ever get washed?
No idea.
Probably no.
I know I'm doing the probs out of order, but this is the logical order to do them in. So that's what I'm done in. Don't worry, we will get to all of the probs. So number 24, the last prob in the chapter, says the eigenstate of A with the eigenvalue alpha is the covariance state alpha, right? So in other words, start this out by saying this. This state is a minimum uncertainty state. We saw that, right? Is the ground state a coherent state? If so, what is the corresponding eigenvalue? And is the time evolution of the ground state consistent with 782? So how do we find out if the ground state is an eigenstate of the lowering operator? That is, how do we find out if it's a coherent state? Well, how do you find out if anything is an eigenstate? You operate and see what happens, right? So, is 0 a coherent state? So what do? We say, okay, let A operate on 0. Okay, but we know what happens when A operates on 0. What happens?
0.
Yeah, you get 0. You fall off the bottom of the ladder. So this is 0. So the answer is yes, it is a coherent state. What's the eigenvalue? 0. Yes? Eigenvalue 0. So that was easy. Okay, now they want to know, is the time evolution of the ground state consistent with 782? So before I actually do that, which doesn't take very long, I'm going to write down what 782 is. So 782, it's on page 265, and it says alpha of t, that is the time evolution of any coherent state, is e to the minus I omega t over 2 alpha times e to the minus I omega t. So that's 782. So how do we find out if the time evolution of the ground state has the time evolution of a coherent state? Well, it has to, because it is a coherent state. We just proved that. But let's find out. What is the time evolution of 0? And that is, what is 0 of t? Of course, it's an energy eigenstate, so, but right? But I know what happens when I operate with any function of the Hamiltonian on an eigenstate of the Hamiltonian. Right? I just get the eigenvalue of h, or the function of the eigenvalue of h. Right? In other words, h operating on 0 just gives me h bar omega over 2, 0, right? Because it's an energy eigenstate. So all you have to do is just evaluate h for this energy eigenstate. And this gives you e to the minus I h bar omega over 2 t over h bar. Canceling out my h bars, I get e, oh, it's times 0, right? I get e to the minus I omega t over 2, 0. Okay, is this consistent with this? Darn right it is, because this is the state 0. So you plug in alpha equals 0 and you get exactly that. Everybody okay? So this was actually a very easy prob. But I wanted to do it in this place because we're trying to make a connection between the coherent states and the ground state, because the ground state is in fact a coherent state. Okay. Okay, so that's 24. Now I'm going to go backwards and do 20, 3. Yeah. Okay. So in 23, we want to find out what the overlap is between two different coherent states, which he's calling alpha and beta. So in 23, we want to find out what the overlap is between two different coherent states. How am I going to do this? Well, I'm going to write down what each of the coherent states is in terms of an expansion and energy eigenstates. So we found out that the coherent state alpha, I get all my constants in correctly, is e to the minus absolute magnitude alpha squared over 2 sum n equals 0 to infinity of alpha to the n over n square root n factorial and the energy eigenstate. So that means that state beta is e to the minus absolute beta squared over 2 sum, and I need another index because I don't want to use n. How about n prime? Ha! N prime equals 0 to infinity beta to the n over square root n prime over n prime factorial state n prime. Okay, now I'm going to take the overlap. In order to take the overlap, I have to turn this guy into the bra. So, the bra beta is, this is just a number here. So I don't change the minus sign here. So this is e to the minus beta absolute magnitude squared over 2, and then sum n prime equals 0 to infinity of. Now here the beta might be a complex number, so I've got a star in. So this will be beta star to the n prime divided by square root n prime factorial and the bra n prime. Okay, so that means taking the overlap of the bra beta with the ket alpha, I just multiply the one equation by the other, and you see why I wanted a different index, right? So bra beta times ket alpha is e to the minus alpha squared over 2 minus beta squared over 2. Those are just numbers, so they commute. Right? Yeah. And then we've got sum. N prime equals 0 to infinity. Sum n equals 0 to infinity of alpha to the nth over square root n prime, n factorial, beta star to the n prime over n prime factorial square root, and then we've got n prime n. Somebody tell me how to simplify this. These are energy eigenstates.
With Dirac delta.
Absolute, not Dirac, but
Delta.
Kronecker. Yeah, exactly. These guys are an orthonormal set. So that means that the overlap between n prime and n is 1 if n prime equals n, and 0 otherwise. So this is the Kronecker delta n prime. So that means that this double sum collapses, right? So I'm just going to get rid of this one. And we just get e to the minus alpha squared plus beta squared over 2, and then sum alpha beta star to the nth over n factorial. Okay, but I can simplify that too, right? Why can I simplify that? Because I know that summation. It's just the Taylor expansion for the exponential. So this is e to the alpha beta star, alpha beta star, yeah. Okay, so, all right, how about beta alpha absolute magnitude squared? Well, it's pretty easy, right? This is e to the minus alpha squared plus beta squared. I don't know, take it in, minus, plus alpha beta star plus beta alpha star. Because I take the absolute magnitude, so I have to take the thing times its complex conjugate. And it's not, I don't have to worry about the transpose because they're both just, beta alpha, the overlap of alpha with beta is just a number. So I don't need to worry about that. It's a complex number though, potentially. Okay, so what does this look like? Well, this is in fact e to the minus alpha minus beta absolute magnitude squared. Everybody okay? Yeah. So this becomes exponentially small when alpha is far from beta. And so so for alpha minus beta very much greater than 1, this goes to 0, which is exactly what we were supposed to find. Okay, so that's 23. All right, so now we've done 21, 22, 23, and 24. We've done 19, 18, 20, let's see, have we done 17? I think we have, possibly, maybe not. Did we do 17? I don't think we did. We did? I know I did 19.
We did 17, yes.
We did 17, okay, great. Okay, so maybe I've done everything except, did I do 13? I must have done 13. All right, I think we've done every one that I'm going to do except 15. And 15 is about the only section that we haven't actually gone through in detail, and that's section 9, solving the Schrodinger equation in position space. So let's start with that, and let's do that actually on Wednesday. So we're going to do Wednesday, we're going to do section 9, then we're going to do section 10 and problem 11, and then we're going to do, and then we'll be done, and that's it. Okay? So please start your PSET from this week, and maybe also if you haven't done the earlier PSETs, might want to get started on those. Bring all your questions on Wednesday, and maybe we'll wrap up this chapter on Wednesday. And on Thursday, on next week, we'll do chapter 8. Any questions? You good? Mostly. I'm really looking forward to chapter 8. It's you're going to love the path intervals. They give you a whole new way of looking at